So what do you get when your priest is too opinionated? A critical mass. Welcome to The Big Puzzle. In this podcast, we explore the subtle connections between science, religion, politics, economics, and history. One piece at a time, we unveil the big picture of this shared experience that we call life. The plan for today is to talk about a bunch of things, so brace yourselves. I will be slightly connecting them, hopefully, but I want you to think about some overarching process or idea or concept, and then we're going to be exploring that and some hopefully practical applications about that. So I want to start by telling a story. When I was a teenager, I was in high school, and one day we were staying at school, and I can't remember why, but at some point we're, I think, in the second or third floor of the building, and I threw the content of a glass of water through the window. And I was looking down while the water was falling, and something interesting happened. So the whole blob of water was falling together, like you would expect, but at some point it looked like it exploded. So looking from above, you saw that thing falling, and then suddenly, drops going in all directions. So that's weird. It felt like it did hit something, but there was nothing. So I tried again, and exactly at the same point, the same thing happened. So I tried a couple of more times, and I realized I was watching something that I never knew it would happen. I never found an explanation. Well, I had my own explanation. My explanation is that, the water can stay together until it reaches some velocity, since it's falling, a free fall, so it's accelerating. And at some point, the friction with the air just makes the water, the cohesion of the water to be overcome by the aerodynamic forces. And that looks kind of an explosion. Maybe the only way you can really see it is like I was doing from above. But if anybody wants to try it, be my guest and tell me if you see the same thing. But that was a kind of a very interesting thing. So while I was doing a little refreshment for this video, I look at, does this have a name? And the only thing I found similar to that is what they call the liquid jet breakup, I think is how they call it. And yeah, it has to do with, like I was explaining, when the aerodynamic forces become stronger than the cohesion of the water. But so since we're talking about water, another thing that I actually did study at school came to mind, and that has to do with the way the water flows. So by trade, I'm an engineer, civil engineer. My PhD is in water resources. So I spend a lot of time studying and thinking about water. But again, when the water is flowing, there's two main ways that it could flow. We call them supercritical or subcritical. And the way it flows behaves differently. So in the supercritical, if you throw a rock into a supercritical flow, the waves will go faster. They won't go back. Right? Because the flow is faster than the way the waves would propagate. But in the subcritical, it's the opposite. You throw a rock, and then the waves can go back to the flow. That's one way you can, describe it. But the interesting thing happens when you're switching from one to the other, and again, it has to do with the slope, and well, the depth of the water, the slope, and the velocity, which are related. So when you have water that's going supercritical, so very fast, and then they reach a change in slope, and that the flow will become subcritical, then you see that there's a lot of dissipation of energy. Think about rapids, right? So rapids are that. So when you see what you call the white water is just water mixed with air that is very turbulent, that is actually the energy of the flow being dissipated really fast, right? When you go from subcritical to supercritical, yeah, it's not that interesting, but that supercritical to subcritical is very interesting. And when you're studying channels and spillways and things like that, those are things that you have to consider because of all the energy that is involved in those processes. So again, this idea of sudden change, of dissipation of energy, you can think about explosions. And while we're talking about explosions, why don't we talk about nuclear explosions? They are probably the most drastic kind of explosion that we can create. And in a nuclear explosion, you're basically liberating energy or turning matter into energy. How does that work? Well, let's say you have uranium, that is a big atom, a lot of electrons, neutrons, protons all together. And since it's big, it's kind of little unstable. So you can break it apart. You can break it apart by throwing something at it. What could you throw at an atom? Well, a neutron would do. So when we generate nuclear energy, what we're doing is that we're just bombarding uranium atoms with neutrons. Now, this is an interesting thing. When the neutron reaches the atom and it breaks, the atom breaks, it liberates more neutrons. And those neutrons could hit other atoms that they would break and so on. Now, there's a certain point in which that process becomes accelerated. And then you have so many atoms broken and so many neutrons hitting other atoms that, you basically produce an explosion. In a nuclear plant, you have some material that absorbs some of those neutrons. So that's how you control that you don't get that situation in which, a runaway or a cascade effect or the domino effect that would create an explosion. But in a bomb, when you want it to explode, well, you need to make sure that you have the critical mass, referring to the joke at the beginning. So it's interesting how the same process suddenly becomes really unstable. Like we were talking also about the water, that suddenly it looks like it's exploding. And well, let's try to connect now water with the different parts of the atoms. And one thing that comes to mind is how the astronomers look for potential places where you could find life. So the first thing that everybody pretty much agrees is that for life you need to have water. Why water? Well, because water is amazing. It's one of the strongest solvent that can dissolve. It's a polar liquid, which also grants it some, and I think we talk about this in some other videos, some unique characteristics. So actually we are 60% water ourselves. You know, in our bodies, it's so important for the chemical processes that happen to have water, and also the water is used to transport, you know, to the cells the nutrients, and also extract you know, all the byproducts, and then being filtered, and well, you know the rest. But it's so important to find water, but water could be in different states. Well, physicists talk about 4, 5, 6, I don't know, I lost count, but we usually talk about the 3 states of water. And water could be as a gas, a vapor, could be liquid, or could be solid, like ice. Right? So the interesting thing is that the only way that water can be used to produce life or to sustain life is if it is liquid. But you not only need liquid, you need that liquid to be able to move. And how does the liquid move? Well, mostly by turning into vapor. And then, so you really need a place where the water could have the range of temperatures to be liquid and also to be as a gas. Right? Not too high, not too low. And that's what they call the Goldilocks zone. So around the star, you have some distance where you assume that, well, in a planet with certain characteristics, you could have liquid water, or the range of temperatures that would allow for liquid water to be in the planet. It has to have gravity strong enough so the water will remain in the planet, but not too high that the water, you know, could compress so much or that, you know, well, other set of issues with having too much gravity like we have in some of the planets in our solar system. But that Goldilocks zone is the first thing that the astronomers look when they find a new star and they believe that they have, that the star has planets. So that this guy that was trying to start a conversation about extraterrestrial life. There was this project, I don't know if it's still alive, it was called SETI, Search of Extraterrestrial Intelligence, that they basically had a lot of telescope or radio telescope looking at the sky and trying to find signals of potential extraterrestrial beings. And but what would you expect? So how many could we have? So this guy, that was Frank Drake, he came up with a way to estimate the number of planets that could have life. And it's what we call the Drake equation. To give you an idea, it's just a set of factors. So you start by, okay, how many galaxies do we estimate that the universe has? And then you say, okay, how many stars per galaxy? And then you multiply those two, and then you say, well, how many planets per star? And then you say, how many planets would be in the Goldilocks zone? And then you keep adding more and more factors, right, to come up with a number. And basically what you could get eventually is a range of numbers. So, okay, in their universe we could have anything between, 500 to 1 million. Right? But it was not just to do a calculation, it was mostly to initiate a discussion about those topics. Now, the idea is really cool, but there's a very big problem. Our planet, you know, see it all around, it's not just in the Goldilocks zone. It has something that is very unique. That is magnetic field. Magnetic field. Why is a magnetic field so important? Well, because life is fragile. As far as we know, life has to have DNA or something equivalent, and that will allow it to replicate and to evolve and everything. But DNA is just a very, very, very long molecule. And the problem with molecules that long is that they can break. How do they break? Well, when they're hit by something. What could be that something that is breaking it? Well, could be cosmic rays. What are cosmic rays? Well, basically are nuclei of hydrogen. So could be protons and neutrons, or could be just protons, alpha particles, that are traveling at immense speed. So even though the mass is relatively small, but the speed is so large that they carry a lot of energy. So if your body is bombarded with these elements, well, your DNA will start breaking. And like we talked in some other video, well, it's very similar to what happens when you age. So you could compare somehow, being exposed to radiation to aging really fast. You die. You die fast. That's why it's very difficult to get to Mars. If you want to look some of my other videos about why we're not going to be colonizing Mars, and especially not having a civilization there anytime soon, so you can now go and look that video. But come back, because there's more in this one. So yeah, that's kind of how we can connect, water, the Goldilocks zone with the elements of the composed atoms. Now, this magnetic field deviates, also captures and deviates those cosmic rays, and then protects us. So that is why it's so important. But while they're doing that, actually around the planet, there's what we call the Van Allen belt. That is where those capture elements are, being moved around. So it's very high radiation zone. And NASA was worried because just to get to the moon, they had to cross that, and they crossed it fast enough they wouldn't have any lasting effect. But still, you see the problem. So now, what is the problem with Drake's equation? We don't know that much about why do we have a magnetic field in the Earth. Yeah, it has to do with the iron core that we've never seen, but we can measure things and deduce that is what is inside of the planet. But how does that create a magnetic field? There's theories, but yeah, you don't know. And also, we know that every 10,000 years or so, I have no idea, maybe a few orders of magnitude wrong, but it switches from positive to negative, from north to south. Positive, negative, from north to south, and some people believe that might be happening soon. So it's complicated, right? Now, if you apply that requirement, that factor of that the planet that is in the Goldilocks zone has to have a magnetic field, but also there's a lot of most of the places in the galaxies, no matter what magnetic field you could have, the the radiation is way too big. So our planet, our solar system, is located in the Goldilocks zone for radiation as well. So you can see that there's a lot of things that makes this experience very unique. Now, is this even real? Or are we just trying to debug the simulation or to understand the simulation? But I believe more in the second. But if it's not, if it's really how the universe works, it's really hard to find another place, even with the trillions of stars that you could have. Those factors reduce that so fast that, you basically, it's very, very difficult to find life anywhere else. But even with magnets, and now we're talking about magnets, let's connect it with something else. So we trust magnets, right? So you say, well, something is a magnet or it's magnetized. You know that it will attract and repel a certain way. But physicists discover that for many materials, when they reach a certain temperature, the magnetism of that element disappears completely. And that's what they call the Curie temperature, because I guess that was discovered by one of the Pierre or Marie Curie. But it's something interesting, right? You have a magnet, then it reaches a certain temperature, and apparently that allows molecules to move enough so they lose their magnetic orientation, and suddenly, you lose the magnetism in that element, in that object. Again, something that, you reach a certain temperature and a sudden change in the characteristics. If we go back to water, we have also something similar. So we were talking about water flowing in channels or in rivers, but even in pipes, you have that. And you could have the water flowing in what is called a laminar flow, where basically all the molecules of water move together. And if you measure the velocity, they follow a parabola, so the molecules close to the center of the pipe move faster, and then as you move closer to the walls of the pipe. Oh, really? Okay. So as you move to the walls, that velocity goes down to zero, and it's zero in the walls, in theory. So that's what we call the laminar flow. And if you can preserve that when it leaves a pipe, you can kind of see it as, as glass. The water is very smooth. But under certain conditions, that laminar flows can turn turbulent. In a turbulent flow, the molecules are all over the place. They're moving everywhere, so everything is kind of crashing to each other. The profile of velocities changes drastically and becomes more, common front. All the molecules in the cross section move at the same speed. But there's a lot of energy dissipation there, right? So you have that laminar and turbulent, and again, the change happens really, really fast under certain conditions. So what would be the overarching concept? Well, we can think it of there's something that is order and something that is chaos. Right? All the things that we talk about, there's something that is order, something that is chaos, and there's a limit. We call that limit a threshold. We call that limit a trigger, a critical mass, or whatever. But there's a certain point in which you go from order to chaos, right? And that, if you look around, you will start seeing that everywhere. So I can look at the trees around me. And you know, once a year, they change drastically. In a few days, they go from being green, and you know, I'm having a lot of processes like photosynthesis happening, to, you know, being lethargic, being pretty much dead, losing their foliage, most of them, the leaves. So, yeah, maybe, you know, in human times, they say, well, it's a couple of weeks, but if you think about longer terms, that's kind of an instant change in the life of the tree that goes over and over. But even worse, so if we look below the trees, we can see that the same thing happens with life. At one point you're alive, and the next you're dead. So all these things don't happen continuously. There's no continuous process. Let's think about water freezing. So water doesn't become, you know, more and more how would I say? I lost the word. Give me a second. The sun is cooking my brain. So not the dense, the viscosity. Ah, my goodness, the viscosity. It doesn't get more viscous. Is that a word? Get more viscosity until it becomes solid. No, at some point it's liquid, and then you go 1 degree below that, and it becomes solid. So all those things happen really, really fast. Now, I said that we're going to be exploring this concept afterwards, after all these examples. And what I want to talk about is our minds. Our minds have the exact same characteristics. One way to describe it is that our minds have certain modules, and we learn to control those modules. What do I mean? Well, for instance, we could say that we have a rational mind and we have an irrational mind. Those are part of the same, so they're just two characteristics of the mind. But if we want to be able to live in society, we need to control the irrational mind, and we need to reinforce the rational mind. We wouldn't have a society if people act irrationally. And usually when somebody acts irrationally, well, they end up being in jail or institutionalized, right? Because they cannot interact. So since we're very young, we learn to shut down our irrational minds as much as possible. But that doesn't mean that we can fully kill it and become like Mr. Spock, right? All rational. The irrational mind is always there. Now, this is an interesting thing. Everything that is worth noting about the universe pretty much happens in that boundary, right, between chaos and order. Right? If not, everything is very boring. But once you get close to there is where all these things really happen. All these Goldilocks zones everywhere, in all aspects of physics, of nature, but also in our minds. So the irrational mind, like I was saying, is always there. And one way, it manifests is with humor. I remember it's been many, many years, probably more than 30, I'm old, 40 years since I read the book, Marvin Minsky, The Society of the Mind. But one thing that stuck to me was that he was talking about the process of humor. And humor requires surprise. So if you want to make something funny, you need to set up something that your rational mind would go to a certain conclusion, and then you provide an alternate conclusion that surprises you. So every joke has to surprise you. If not, it's not funny. That's why many people now that supposed comedians are not really funny. They might tell you what you want to hear and you would celebrate that. So think about late night comedians, but they're not really funny. They're not surprising you. They're not disrupting your rational mind. So your first reaction is surprise, and then is laughter. That's why when you're walking in the street and you see an old lady falling, you know that the situation is awful. Your rational mind knows that it's awful, but it's likely that you will chuckle. And then you will feel terrible about that chuckle. But that's just your irrational mind, right? Because you don't expect all people to fall. And that disruption of your observation, your logical conclusion of what you're seeing, it manifests as surprise and as hopefully a small chuckle. Now, if you're still laughing 5 minutes afterwards, well, that's on you. But it's so interesting that humor happens in that. I coined this saying myself. So if you want to quote me, you can say that I said it first because I never heard it from anybody else. But I define laughter as the celebration of the irrational mind for defeating the rational mind. So that is laughter. Your irrational mind is free, finally. Right? Ha! Rational mind, you didn't see that coming. Right? So it's their liberation. But like I was saying, it's important to explore that limit between order and chaos, irrational and rational. And we usually call that creativity. Creativity happens when you can go from your rational to your irrational modules of your mind back and forth. Right? And you get ideas, new ideas from the irrational mind, and then you validate them or refine them with your rational mind. I heard this from Salvador Dali, the artist. But then I heard that Einstein did something similar. I don't know if that's true. So the way they explored their irrational mind was they would try to fall asleep sitting on a chair and having, I think Salvador Dali said that he had a spoon in his hand. So when they start to fall asleep, it's a good place where your irrational mind starts to manifest. Your muscles will relax, and you would drop the spoon. And he had a plate or something below that would make a noise that wake him up, that he would still have a recollection of what he was experiencing 1 second before that. And they said that Einstein did the same thing. I don't know. But that's a way that they could, when we say about the oniric, has to do with dreams and nature of Dali's work. Other people, musicians, for instance, many musicians, they use drugs for that effect. They get drugged and then the irrational mind manifests and then they become creative. I completely dislike that. For me, that's like cheating. You're not really being creative. You're using substances to do that. So, but there's a lot of people that actually can become creative. They develop that capability to explore those limits, which are irrational minds. Now, those people live pretty miserable lives. And let me tell you why. I was talking about society. Society is about rules that we all agree. It's about expectations. It's about extending my hand and expecting the other person to extend their hand, and we do a handshake. Right? All those unwritten rules about how society works is about me smiling and the other person smiling back. All those things, ranging from written rules or laws to everyday things. But you have to rely on that predictability. And that only happens in the rational realm. When you're interacting with somebody that's very creative, that are often visiting their irrational part of their mind, well, their behavior will look weird. We have this idea of the mad scientist, right? So somebody that's distracted all the time, and you can't understand that they can't explain themselves, because irrational minds cannot explain themselves. That's why they're irrational. If they could, they would be rational. But creative people are by nature disruptive. They look at the problems from a completely different point of view. And that's how they find new solutions to the problem. So you have this dichotomy. You really, really need creative people in society, but everything in society is built to deter people from being creative. Right? So, what advice can I give? I think we need more creative people. I think it's something we're losing. We are every time. So one way where the irrational mind manifests is when we're bored. Not only when we're falling asleep, but when we are bored. And think about the creations of one of the most interesting theories. So Isaac Newton, he was just sitting and he saw an apple falling, and then he said, well, why did it fall? Is it the earth attracting? It looks like the earth is attracting the apple, but wouldn't the apple be attracting the earth? And so that triggered his mind, with his extremely brilliant mind, that he came out with a gravitational theory. Think about Einstein. So Einstein mentioned that he started thinking about the relativity when he envisioned himself riding a ray of light. And, that's how he started thinking, well, maybe how would I see things if I would be moving at the speed of light? So all these things came when we are bored. Now, today's society is preventing us from being bored. You have your phone in your hand all the time, not watching videos like this that hopefully will make you think a little. According at least to the analytics of these videos, you're most likely not watching this video. But if you are, think about getting more bored. Think about getting your phone out, learn to be more creative, learn to trust your irrational mind in, a controlled way. Maybe not doing that when you're having dinner with your family and you're distracted thinking about traveling in a rate of light. But in other, just set some time apart to be irrational, to let your irrational mind manifest. Explore humor, explore ridicule. And I'm not talking about doing it for people, but the concept of being ridiculed, making no sense. Right? And know that it will hurt you. Know that if you succeed at that, you'll be rejected. But you will be an essential member of society, and you can make really important contributions that you will never make if you're just killing your boredom and your creativity all the time. Well, I think this has been long enough. It's very hot. And yeah, I think that my irrational mind is starting to take over. So before that happens, I hope to read some of your ideas in the comments. And yeah, hopefully see you in the next one. Bye.